Hello and welcome to Golden Geography. Today we're going to be thinking about ice sheets, particularly the Laurentide ice sheet, and what impact it had on Minnesota. So here's the spec bit. We are looking at case studies, particularly looking at a landscape associated with the action of ice sheets, and at least one from beyond the UK. So for our case study here of Minnesota, we're looking at the Laurentide ice sheet, and we're looking for these three key things. We are thinking a little bit about the physical factors which influence the formation of landforms within this landscape, the interrelationships between the different landforms found within this landscape, and then how and why landscape systems can change over time, over long periods of time, millennia, but also very short periods of time, seconds, or even seasonal changes. We're going to be thinking about the physical factors to start with. We're going to be thinking a little bit about how they influence this landscape system. So we have a little list here. It's important to go back and have a look at your previous key questions for the background towards these key factors we're looking at. So we have physical factors that are including geology, climate, latitude and longitude, altitude, aspect and relief. So if you don't know what those are, go back and have a look at those in your previous videos. But here we're going to apply them specifically to Minnesota. So we're going to start with the geology. We have a map here of Minnesota that shows quite a significant variation of geology within it. We find to the north, particularly to the northeast, that we have alternating belts of igneous rocks and metamorphic rocks. These are quite resistant, so we do find some erosional features in this area as a result of that. We find more sedimentary rocks further south in the middle and southern parts of Minnesota because they have been developed as a result of deposition, both by the ice, the glacial ice, but also by meltwater and glaciofluvial processes. So it's a little bit of a north-south divide here, and you can see if you look at the key there's a significant variation within those two. But the geology is important because it influences the landforms we find. We also have to be aware of the climate. The climate today ranges anything from -11 degrees centigrade in the winter right through to about positive 23 degrees C in the summertime. So it's quite a significant temperature range that Minnesota experiences today. But in the past, that would have been slightly different. Those temperatures would have been significantly lower. And that's important because if this area didn't have those colder conditions, then particularly during those summer months, the ice would not have existed. And the ice did cover large portions of Minnesota. So majority of the time during the last glaciation, those temperatures would have been below freezing, enabling those ice lobes to exist. And as you can see from the image, we have 4 key lobes: the Rainy lobe, the Radina lobe, the Superior lobe, and the Des Moines lobe. They have influenced the landforms that we find. So the climate that enabled them to exist is really important. So particularly those past climatic conditions, those ice age conditions, have influenced the landforms we find here. Latitude and longitude. Here we're really just looking at the location, and it's really that kind of 43 to 49 degrees north. And that's the important bit. It's far enough north that during the last ice age it was covered by an ice sheet, but far enough south that it wasn't totally covered, that it was on the margins of that ice sheet, that those lobes could advance and retreat and could generate both erosional and depositional landforms within this area. So its location, that marginal location, is important to the landscape we find. Altitude is important too. On average, the majority of the United States is about 760 meters above sea level. Minnesota is significantly less than that. It's on the lower side in terms of of altitude for the US, but it's not the lowest. So there is significant variations across the US, but also within Minnesota. If you look at the geological map of Minnesota, we can see, particularly to the northeast, there's quite a high altitude, and those areas were eroded, whereas if you went to the south, the altitude is much lower, and it's much flatter land, and that's an area of deposition that we have there. What is interesting is that scientists have estimated that the Laurentide ice sheet, in places particularly where those lobes were potentially up to 1 kilometre thick, and the thickness of those lobes have eroded even those areas of high altitude by about 500 to 700 metres. So it's a significant amount of erosion that has happened across Minnesota, but particularly in those areas of high altitude today. If we think a little bit about the aspect and the relief, this has very little impact on the south, which is relatively flat, but it does impact the north. So the areas which were eroded and had valley glaciers and processes associated and landforms associated with that, those mountainous areas, are the areas of high relief in the north and the east, and are the areas that, because of that relief aspect, played a key part. So those north-facing areas would have had shade, and in those north-facing areas, snowfall would have produced ice, and you would have had the development of glaciers and valley glaciers because of the aspect that we have here. Okay, let's think a little bit about how we have a relationship between different landforms within this landscape. We're going to start with ellipsoidal basins. Ellipsoidal basins are areas where you have significant erosion of the landscape. They tend to have formed beneath the accumulation zone of your ice sheet. So whether the snow became ice and the ice sheet was at its thickest, the heart of the ice sheet, that thickness and that pressure it put on the land beneath it would have eroded it and created a deep basin shape. And that basin, that ellipsoidal basin, once the ice sheet melted away, has been filled with rainwater. So it forms a large lake. And the best example we have is Hudson Bay, which is, as I said, was where the heart of the Laurentide ice sheet was. You also find, particularly associated in terms of Minnesota, the association is with lobes, and those lobes, as they retreated, deposited drumlins. So we're moving away here from the heart of the glacier, moving more to the margins of the glacier, and where those margins moved and they generated lobes, those lobes that produced drumlins, where they protruded over the land and moved forward and backwards. When they retreated, they produce drumlins. They can be up to 2 kilometers or 1¼ miles long. They are directional, so they indicate the direction of retreat of those lobes. And there are areas, particularly in the northeast, where there are significant numbers of these. And they are found with other depositional features like till plains, moraines as well. And not just in that region, but wherever there were lobes, you could find these. And with ice sheets, you will tend to find multiples of them, so drumlin fields or baskets of eggs. Those lobes were also really important in depositing till sheets. Where those lobes came across Minnesota, they deposited till that had been eroded in modern day parts of Canada. So the material had been moved thousands of miles and then dropped by those lobes as they retreated. And these till sheets cover vast areas. And as you can see on the diagram, there's two very distinctive variations that you can see here, the grey and the brown, different types of till that we are finding in Minnesota. We also have kettle holes. These are developed where very resistant bits of ice are not melting at the same rate as the rest of the glacier or the ice sheet. And these resistant bits of ice stay in place as the rest of the glacier melts. And as that glacier melts, the meltwater will deposit material and develop an outwash plain. And only eventually those really hard resistant bits of ice will melt away, and they will leave behind, where they stood, kettle holes. If those kettle holes fill with water, they will become kettle lakes. That might be rainwater or meltwater. And in terms of Minnesota, there are a significant number of these. Otter Tail Country has lots of them, over thousands of these. And it's one of the most distinctive features that Minnesota has, in terms of not as many are found in other parts of the US. Minnesota has the largest number of kettle lakes and kettle holes. Now, how do these all relate? It's a lot harder to look at how these relate to each other than it would be if you were looking at a valley glacier. Valley glacier and the landforms there are a lot more linear. You don't really have that in the same way. You do have that starting point. You do have your ellipsoidal basin, which is the heart of your ice sheet. But ice sheets don't move in one direction. They spread out in all directions, which means we have to look at the margins to see if there's any relationship between some of the landforms, the depositional landforms particularly. So we are looking to see what happened at those lobes. And as we've already mentioned, those lobes deposited drumlins and till sheets and kettle lakes. So we will find these key features in the same area formed by those lobes on the margin of that ice sheet. Sometimes you find them together, sometimes separately, depending on the lobe and the energy and lots of other factors. But they are found together rather than in a linear progression. Okay, last bit. How and why the landscape system changes over time, from millennia to seconds. So if we're talking about landscape changes, how has Minnesota changed? How has any landscape changed? Well, if you're looking at millennia, you're looking at very slow processes. You're looking at erosional processes. And if you look at the image on the left, you can see that most landscapes start relatively flat. There might have been some sort of tectonic uplift, but the area of land would have been flat. And probably there would have been some sort of river that would have drained through and eroded that landscape, creating V-shaped valleys. Well, if that landscape was then covered by an ice sheet, or even just valley glaciers, you will have found that those rivers would have been replaced by glaciers, and that ice is much stronger, its erosive power is much greater. So you can see on the image on the right that actually it would have widened and deepened those V-shaped valleys, making them into U-shaped valleys. It takes a long time. And if we look at an even bigger scale, if we go back to think about our ellipsoidal basins, these are massive, continental scale. They would have taken millions of years for that level of erosion to have taken place, to deepen that basin, to create that shape. So some of these landscapes really do take very long periods of time to erode. On the flip side, during both ice ages and today during this interglacial, we can get features and events that happen really quickly. The landscape that we have, when it's been deglaciated and is exposed to the atmosphere we have, our climate, particularly if that climate has temperatures fluctuating around zero, will experience weathering. Particularly freeze-thaw will help to break up some of that landscape, and it will produce smaller bits of debris, and if there's enough debris that breaks up, then eventually you'll get a rockfall. And they happen really quickly. They can happen in a matter of seconds or minutes, and they will change the valley sides or the back wall of a quarry when those rockfalls happen. You can also find changes that happen over seasonal periods. If you're looking at depositional rates, particularly during periods of deglaciation, you will find that during spring and summer you'll get more rapid deposition because there's more rapid movement and erosion, there's more energy in the system. than there would be in winter. So there can be seasonal variations in deposition that helps form our depositional landforms. Anything from kames and eskers through to moraines can witness those seasonal changes. They can also be changed if you get an advance in a glacier, which is unusual, but it can happen. You can find that the glacier advances, it will effectively rub out, modify the landscape in front of it as it advances. The last thing that's really interested is Jakob events, or glacial outburst events. And the image we have here on the right shows that. It's something that's very rarely witnessed, but there is evidence in our landscapes that have happened. So we find very deep V-shaped trenches and debris fans, and it's effectively where, as the glacier has melted, meltwater has built up behind something. It might be a very hard piece of ice, or it might be, in this image, a bit of moraine that suddenly gives way, and you get a big surge of meltwater that can challenge the landscape, can produce big depositional sheets of material, outwash sheets, covering vast areas. So there can be some events that happen really quickly. Okay, I've got some quick questions for you. Pause the video, see if you can answer these 8 questions. If you're not sure, feel free to rewind and have a little look at the video to find the answers. Okay, check your answers. Here they are. See if you've got the right answer, and if not, go back and have a look again. I've just put together a few of the essays that have come up on the OCR physical environment paper in the past. The 16 mark ones are from the A level and the 14 marks are from the AS. You should be able to answer questions here using your Minnesota case study, but please remember you need to have context. So you need a bit of theory first before you then put in your case study. And after your case study, you need to make sure that you do some AO2 work, some evaluation or analysis of the information that you've written about. All right, thank you for listening.